we are calling SLA like. And second one is a material extrusion, that is FDM. In this there is a one printing technique, FDM, fuse deposition modeling. The third one is powder bed fusion. Fourth is binder jetting. Fifth, material jetting. Sixth, direct energy deposition. So we will start from wet photopolymerization. The especially stereolithography, which was the first ever additive manufacturing technology, developed in approximately 1980, I think. The process based on the solidification of a liquid polymer using UV laser or light source. So light source laser beam traces a cross section of the part patient on the surface of the liquid resin. SLA elevator platform descent. And if we talk about vat, how it's work, so a vat or tank is filled with the liquid photopolymer resin, that is called photopolymer resin, and a high precision UV laser scan the surface of the liquid, selectively curing and hardening specific area as per the 3D model cross section. Once a layer is cured, the build platform move down. The build platform moves down and allowing the next layer to the cure. So this process repeat until the final object is complete, followed by the post processing. Like post processing is like once product is manufactured, there is a process of cleaning, or we can say UV curing and surface finishing, that is known as a post processing process. So now moving on, the next one is, that is material extrusion, FDM, that is known as also FDM is fuse deposition modeling. So fuse deposition modeling is most common and affordable AM process, we can say, widely used for rapid prototyping and functional part production. This process is also known as a simplicity, we can say accessibility and material efficiency. So material is drawn through, if we talk about how it's work, so first of all, material is drawn through a nozzle where it heated and then deposited layer by layer. So in all the processes, what we are going to discuss, in all the processes, the layer by layer word is going to be a common, because in additive manufacturing we will manufacturing layer by layer. So a plastic, we can say there is a plastic, if we talk about how it's work, plastic filament typically ABS, PLA or PET, heated and extruded through a nozzle. The nozzle move in a predefined path, deposited the molten material layer by layer onto the build platform. Each layer cool the solidify, the next layer is added on the top. If we talk about advantages of the FDM, so FDM is popular due to its low cost, ease of use, and ability to print a large object. We can print large object as well in this mechanism, and however it has a lower resolution and surface quality compared to SLA. Additionally, anisotropic properties, a big bond between layer, may impact the mechanical strength of the printed part. If we talk about application of this FDM, so we can say in education, prototyping, automotive, aerospace, and consumer good. Many engineers or designers, we can say, and researchers rely on FDM for functional testing and design validation. So moving on, the next, that is next additive manufacturing technology, that is powder bed fusion. So powder bed fusion encompass multiple high performance AM processes, including selective laser sintering, selective laser melting, and electron beam melting. These methods use a high energy laser, or we can say electron beam, to fuse a powder material together, forming solid object layer by layer. And selective laser sintering is a high power laser to fuse powdered thermoplastic material like nylon, TPU, and the laser selective scan, the powder bed sintering, partially melting the particle from each layer. And since the surrounding unsintered powder act as support, does not require additional support structure. If we talk about advantages of the powder bed, so it is a strong and functional part with good mechanical properties, ideal for batch production of complex geometry and interlocking part. And if we talk about application of the powder bed fusion in medical implant, automotive part, and aerospace application due to strength and material flexibility. And now, moving on, binder jetting. So, binder jetting is a unique AM process uh, that does not require heat during printing. In this, we don't require a heat. Instead, it is use a liquid binder to adhere powder material together, forming the 3D object. There is a if we talk about the working principle of the binder jetting, there is a roller, and a roller spread a thin layer of the powder on the build platform. There is a platform, and in this we will spread the powder, and that layer will spread the powder throughout the platform, and the printed selectively deposit a binding agent, bonding the powder particles in a specific area. This process is repeated until the object is fully formed. As we can see from the diagram, the final part is then post process. Again, in this also there is a post processing. For each and every process, we will do the post processing, and that post processing is known as a cleaning, we can say. And in this centering, infiltration, or coating to improve, then after once product is manufactured, if we want to improve the strength and durability, then we can go for the coating also. And if we talk about the application of the binder jetting, so it is used for full Kohler 3D printing, sand casting mold, and metal part production. We can use for metal part production in industry such as automotive, aerospace. Now, moving on, material jetting. The next printer is a material jetting process. So, material jetting is a similar to inkjet printing, but instead of ink, it jets photopolymer droplet onto a build platform, which are then covered using the UV light. So, the print head is positioned above the build platform. If we talk about how it's working, so multiple print heads spray tiny droplet of liquid photopolymer onto the surface. UV light instantly curves and solidify the material. And this
Hello.
process, uh,
Hello.
yes,
Excuse me, sir. Sir, slides are not changing.
okay, okay. Thank you for the confirmation.
Sorry
I
for
will
the interruption.
no. Okay, okay. Thank you. Uh, Now it's changing. Direct next method is direct energy deposition. So direct energy consists of a nozzle mounted on a multi-axis arm. Nozzle can move in multiple directions. Material is melted upon deposition with a laser or electron beam. So direct energy deposition is also called DEED and is primarily used for a metal part, repair, reinforcement, and large scale manufacturing. And we talk about working of the direct energy deposition, a focus energy source. There is a laser electron beam, or plasma arc, we can say, melt the metal, powder, or wire as it is deposited onto the workpiece. The material is built layer by layer with the energy source precisely controlling the melting and bonding process. So application of the direct energy deposition used in repairing turbine blade, aircraft part, and large industrial component. It is also gaining traction in aerospace and defense sector due to its ability to manufacture large complex metal structure. So moving on the next part, that is material used in additive manufacturing. There are a few materials that we are using in the manufacturing like polymer, metal, ceramic, composites. So that these are the few metal which we are using. Polymer, one of the most we talk about polymer. Then polymer most commonly used material in AM, particularly for prototyping, consumer product and functional component. Polylactic acid, that is PLA, we can say, and is widely used to is biodegradable nature, making it ideal for educational model and decorative object. However, it has a limited temperature resistance. So that one of the other hand is stronger and more durable. Now we talk about metals. The metal, there are many metals like titanium, stainless steel, cobalt, chromium, nickel-based alloy such as Inconel 625 and 719 are ideal for jet engine, gas turbine, and energy sectors component. Metal AM processes uh, such as laser melting, electron beam, and direct deposition enable price efficiently manufacturing for complex metal part. Now, if we talk about ceramics, applied in electronics and biomedical applications. So, ceramics primarily used for application requiring a high temperature stability, wear resistance, and chemical durability. Alumina and zirconia are widely employed in uh, biomedical implant for coating purpose, or in aerospace component there is zirconia, we can say, and cutting tool due to their exceptional hardness and thermal resistance. There is a silicon carbide and silicon nitride. These are also the ceramics and used in electronics heat exchanger and high performance nozzle because of their superior thermal and electrical properties. Hydroxyapatite, one of the another ceramics powder, which is biocompatible powder and is used for especially used in bone implant and dental applications due to its ability with the human tissues. Now, composite enhance mechanical property with fiber reinforcement. So, composite are another critical material category name offering enhanced mechanical property through the combination of two or more metals. So, there are few composite like carbon fiber reinforcement, and there are many more. So, now moving on the next, that is present condition and trends.
Hello,
So,
sorry for interruption, Jaskaran sir.
yes, yes,
Hello,
sir.
sorry for
Yeah.
interruption. Your PPT is not moving, sir. Slides is not moving.
Now, sir, is moving.
Hello.
Sorry, there is a internet connection issue. Due to that, maybe it got stuck. Now it's moving. Am I audible?
No, sir. No, sir.
Not audible. Maybe I'm facing. There are some kind of internet issue in my area. There
No,
is
it's
going.
not an internet issue, sir. It's a PPT presenting issue.
Okay. So I can say a reshare again.
Yes, sir. You need to reshare. Yes, sir. Started. Now visible, sir.
Okay.
Visible, sir.
Thank you. Thank you for the confirmation. So I was discuss about the technology and research. The model data is usually in stereolithography format. It first decomposes into a series of 2D finitely thick cross section, which are then fed into an AM machine, used directly and indirectly to produce prototype part, reduce manufacturing and product cost. So there is a future aspect we talk about. Then a future of AM is bright. Researchers are developing a new material with enhanced properties, including high strength alloy, biocompatible polymer, even multi-material printing capabilities. The integration of artificial intelligence and automation expected to improve process efficiency and reduce effect. So university industry collaboration and technology transfer. A more and more company have begun using AM technology to reduce time to market, increase product performance, cost, and Another major hurdle in the performance of fabricated part, while AM enable the creation of complex geometry that are impossible with the traditional manufacturing. The mechanical property of AM produced part often do not match those conventional manufacturing component issues such as porosity, anisotropy, residual stress, and lower fatigue stress. So there is some education and training required for this. Educating the general public about the AM empower people to build what they dream. Former AM education has already been integrated into a curricula at different level. Education material on rapid prototyping having long been a part of manufacturing engineering courses. So there, I have already discussed the AM future aspect, thrill industry revolution, the cost-effective mass customization of complex product, reduce material-based and energy consumptions, adopt new product design without the additional expenses. In the biomedical field, AM can be used fabricate tissue scaffold that are biocompatible, biodegradable, and bioabsorbable. So, looking ahead, the future AM is bright. The integration of artificial intelligence and automation expected to improve process. Now, there is gaps and needs, material development and evaluation, system integration and cyber implementation, material development and evaluation, design methodology and standard, modeling, monitoring, control and process, characterization and certification. So collaboration, university, industry collaboration and technology transfer. To compare with the conventional mass production process, AM technology must advance significantly to drastically reduce the cost of fabrication, improve the performance of fabricated part. The price of material for AM would need to drop substantially in order to achieve a sufficient return on investment to make AM for mass production reality. A key factor that must improve the AM to be widely adopted in mass production into the cost of material. Currently, AM material, whether polymer metals or ceramics, are significantly more expensive than their conventional process counterpart. For example, powder used in AM can cost 10 to or 100 times more than the same material in a bulk form for casting or machining. Additionally, many additive manufacturing process require high purity, especially a prepared material, further driving up cost. If material price can be reduced through the advancement in supply chain, alternative material source or recycling technique, AM could become more economical, viable for large scale production. To achieve a sufficient return on investment for AM in mass production, innovation or need in process of automation, print speed, multi-material capability and post-processing, the integration of AI-driven optimization, hybrid manufacturing, technology and post-processing, the integration of AI-driven optimization, hybrid manufacturing technology, combining AM with conventional method and advance in high-speed printing technology could significantly enhance AM competitiveness. AM offer a unique advantage such as design, flexibility, reduce material efficiency and performance reliability to rival traditional manufacturing high volume application. As research continue and technology improvement emerge, the future of AM in production, the promising but require a strategic investment and breakthrough. So, taking a full advantage of AM will require educating the current workforce, recruiting a new generation of student, developing a proper design tool. Recommendation, technology and research, material, development of new material for AM process, formation and mixing of material in desired form with the desired property design.
So sorry for interruption. So just in this process, so we are having a different kind of printers are available. So in this case, so there are a lot many modules are available for FTM. So basically, this printer, the working phenomena of printer is working on layer by layer, basically. And there are such kind of application like in aerospace industry, automotive industries, healthcare, customer goods. So there are some benefits of the using this 3D printer. So priorly, the main benefit is customization. We let's say the basic requirement of this to work with any prototyping is to create a 3D model first of all. So it can be of the any CAD software. So can be we can use any CAD platform like Fusion 360 degree is right now a very hot topic in the market. So we can create a model by Fusion 360 degree software. The other one, SolidWorks is there. Creo parametric software is also there, and next CAD software is also there. So in all these softwares, so we can able to create a customized model for the 3D printing. And once we got 3D printing, so other benefit is reduce wastage. Reduce wastage in term of you can simply say that wastage in term of material, wastage in term of manpower, wastage in term of machining cost, wastage in term of material management, inventory. We need not to store material in the long stores for making any part or any component. So that is why it is the reduced weight. And other one is rapid prototyping. Why it is called rapid prototyping means same day you will get a model. Like by morning, if I think we can design that model, so by the same day means by the evening, depend upon the complexity of the model. So we can able to get a model immediately by the same day. That is why it is called rapid prototyping. And the basic phenomena of working with this 3D printing is just it is working on the layer by layer phenomena. It will make a layer, and even we have SLS technology that we can cover up later on. SLS, SLA printing technology is there. So on all these technology, your part will make a layer by layer. So the so in the future trends, it is technological advancements. So that's my topic to for the today. So it's a future trend for the same is technological and advancements. So in this, maybe I would like to add in case of 4D, 5D printing, there are some more technological materials are available, like they are called the smart materials. So I will discuss this later on. So basically, the second point is in the future trend, every company we talk about the home appliance company, we talk about that automotive industry, home appliance industry, any rubber industry, shoe industry, then daily customer good industries. Then in all the automotive sector, growing demand for customization means if the company launches some model like in January, and they need to relaunch the model in the June only, because if they are unable to create a new model, the customer will not satisfied. So that is why they are rapidly going to create a new model day by day. That is a growing demand for customization. And in any of the model, 80% functionality will the same. It will remain same, and rest 20% will be the changed one. Means they if the function is same, let's say mobile phone. So if the entire screen, entire UI UX space is same, but right now companies are customizing the basic shapes of the mobile. Like they will make it thin, they will make it wider than the previous model. They will install one or two cameras. Simply take the example of iPhone. Right now, from the past 10 to 15 models they have launched, and they have just created a new sense of model, like growing demand for customization. They have customized the previous design. So on that design, they have just modified that camera, that they have just modified the location of flash. They have just modified the location of notification tab. So it is all called customization, and it is only possible with the 3D printing, because rapidly we can get a model and we can easily be customized the same model. So sustainability of and material efficiency. is I already clear you about the same thing, because we need not to store any inventory. We need to work with the sustained materials. Like there are a lot many materials are available, like PEEK, PET-G material, PLA materials are available, and all materials are fully sustained materials. They can easily available, and they can sustain up to long type of time. We can even test those rapid prototype models. And in industry 4.0, right now 5.0 is already started. Digital manufacturing and integration, it helps a lot in digital manufacturing. Digital manufacturing means to say start from the zero of the model, so we can start with the raw and up to the final stage. We need not to spend a single penny onto the wastage, like materials wastage, like any tool cost. Everything is digitalized, and we need to take the help of number of different softwares. So on that softwares, so that's basically we call it industry 5.0. So we can program the robots, we can make a design, so we can digitally manufacture and integration everything. So these are some future trends of the same. And the material innovation is again very modern concept for this 3D printing, because if we talk about you can say that 12 to 15 years past, so there are some powder technology materials are available. This is basically it is SLA, it's a selective laser sintering. So in this, or this is also called stereolithography sintering, and that powder is available, and the laser fall down onto the powder, and on which area, up to the designated area where the laser fall down, basically it will solidify that powder. So it is basically the customized model, and whatever model we have designed, we will send the same model for the encoding to the laser, and the laser beam will fall according to the model parameter, and it will immediately solidify that powder technology. So on that, the strengths are not there. So it is basically just a visual attraction of the model. If you touch the model, it will immediately break down. So by the 10-year pack, and nowadays we can easily say that there are composite materials are available for the 3D printing. Even the metal printing is also possible, and there are a lot many research area are there in the material innovation. So we can be able to customize that material, and we can make 100% accurate model. That we will, let's take one example of that jet molding. So when the aircraft is going to manufacture, so talk about the Boeing. So Boeing plane is very huge and very big in design, and for to make a Boeing plane itself, so engineer needs to ready at least 1 lakhs mold for the components. For the aircraft, they have to easily make a 1 lakh to 1.2 lakh molds for each component. And once it will be launched in the market, means aircraft launch in the market. So after 2 years, the company will build a new model. So meantime, all molds are useless. So they will not be able to manufacture any big or any jet planes or any Boeing planes. So the molds are useless. So the engineers, they have what they have decided. They have just take a component, like in that inside of the airplane, there are the windows, like 180 or 360 windows. They have to make in the plastic, and they just make a composite fiber, and they just put up in the 3D printer, and the 3D printer will directly give that windows model, the real model of the window, with the carbon fiber or with the composite material. So they are stronger, they are lighter, they are actually behave like the molded component. Means they have directly neglect that, or you can say that directly eliminate the cost of the mold. Means the company need not to work for the mold. So they have directly designed the model, they have directly print. Means if we need a bulk production, then mold is required. If we need a component in a short, like we want only 200, 300, 400 components to be there we can make a smart material as we require. Like in the metal, there are composites are available, plastic in the fibers are available, PET G material. It is suddenly prove that PETG material is having a great strength than the ordinary plastic. So you can directly print that model, and it behave like 80% great strength than the plastic model. So biocompatible materials for the medical application, this is a very good topic nowadays. So bones, even organs are going to print with the help of this biocompatible materials for the medical application. So it is a very we can say that the upgrowing field in the field of material for biomedical application. The core research area is there in the biomedical for the mechanical engineers specialized. So they can evenly take one material. So basically, it is a parameter of 4D printing. So on this biocompatible materials, so we can be able to print organs. So that behaves or that function when if someone, let's say, his gallbladder of the patient is not functioning properly, so doctor just take a blood sample from the patient. So by taking a blood sample, they will develop a tissue. So by the next 30 days, they have developed the tissue. We can put up the same tissues of whatever they have artificially developed from the blood to the machine, and machine will print a gallbladder. We can remove infected gallbladder from the patient, and we can install the new one printed gallbladder. So this is a biocompatibility compatible materials for medical application in the bones also. So sustainable materials, and they are the recycled and biodegradable polymers are also there. So polylactic acid, like PLA material, so they are biodegradable. And materials in the 3D printing, lot many materials nowadays, we can say that more than 35 materials are available, and in the category of all those 35 materials, they are subcategorized into the 150 plus kind of different materials are available for this 3D printing. So it is all about the material innovation. Hybrid manufacturing system, I think you all know about the hybrid manufacturing system, integration of additive and subtractive manufacturing. So it is possible we can be make half of the model in the 3D printing and rest of the model in the CNC. So it is also possible in nowadays with the hybrid manufacturing. So it improved precise and efficiency. So single machine solution combination, multiple manufacturing methods. So what it suggests in the single machine, so we can be able to utilize the multiple manufacturing methods on the same topic. So on the same part, like I'll give you one example. Let's say one plastic cap is there. So on the plastic cap, so it needs to fit on the bottle. So we need to have a thread of that metallic one. So outer casing is the plastic and inner threads are from the metal one. So we can be hybrid manufacturing that cap in the machine itself. It will make a metal part, it will make a plastic part. They it will club together, and after printing gets done, we can remove the model from the machine workbench, and we can put up to the CNC. So it will make a thread. Even also we can make a threads itself onto the 3D printing machine. So that kind of hybrid manufacturing system is also available. So we can be simply say that it is well possible to manufacture or well mannered way we can be able to manufacture with the two or three materials, and multi-jet fusioning is available for the same. Multi-jet fusioning is available for the same 3D printing method, but it is again working with the layer by layer system. So it increase use in production, shift from prototyping to full scale production. So this is very good point. So shift from prototyping to full scale production. So this point itself understand for, so if we need to we have one sample, we need to have one sample for that, for to make that sample. A lot of engineers, they are used to take the help of wood, they used to take the help of POP, used to take the help of that subtractive manufacturing on the shift base, and they just make the all models on the CNC, And by taking those models, a lot many shifts, a lot many workers they have spent to make a one model. Lot many machines are occupied for making a one model. So it, in this case, it will decrease that cost. So in term of machine, in term of worker, so it is shift from prototyping to full scale production. Like we can be able to uh, fully manufacture all the component by having a sample with the rapid prototyping. So mass customization for good consumer and daily use items, we can be able to communicate it uh, in the well manner. Like we have make a lot many models with the mass customization for consumer goods. So we can be see that if we talk about the TV, so start from the TV, LCDs are coming. Earlier it was black and white TV, so then color TV, then LEDs are there, then sorry, LCDs are there, then LEDs come. Right now in the market there are a lot many models: 4K, Ultra HD, ultra wide. These are the models are available. It is only possible by having a prototyping in the rapid way, so we can be able to mass customization for the consumer goods. It is possible. So it is only possible if we are having prototype with us. So uh, if you have any question, then you can ask me. I'm ready to answer. So automation and AI integration, this is again very good point, because nowadays AI driven generative design tools are available. So in the artificial intelligence, so we can create a generative design tools. So nowadays generative design is a very hot topic in the industry. So I would like to clear about that, this generative design, what this actually. So in the generative design, let's say I'll take one example. A lathe machine bed size is 100 by 100, for example, and 100 by 100 inches. Let's say I'll give you one sort of example. So if the weight of that lathe bed is suppose 1 quintal, and it is we and nowadays what generative design is basically does, it will create the same bed size 100 by 100 in inches with the reduced weight capability. So by taking care of computer aided engineering itself, by taking care of load acting on the same bed, by taking care of all the stresses, they have just eliminate that unwanted weight from the bed. Even talk about that chair, talk about that table, we can talk about that vehicles. It is not a big challenge for the Indian market, that if any vehicle need to be manufactured, so the Indian people are uh, l- very much satisfied if the vehicle is having a good mileage. The mileage only comes with the if the vehicle weight is reduced, if the vehicle is lighter in weight, and it is only possible if the companies are, let's say, talk about a simple example of nano. If the nano car they have manufactured under 1 lakh, so they just eliminate that unwanted weight. You unnecessarily they have eliminated the weight, and what happen actually, the strength of that nano means it is not a even safe car, and the safety it get 11 stars. So almost 11 stars mean to say that the safety factor is very bad. And in the Indian cars, so we can evenly target to the 89 90 stars. So that car got 11 stars only. So in the safety, why? What's the reason? Basically, they have just reduced the material everywhere. Unwanted material they have reduced just to save the cost of the car. And in that, basically, what happened? They have not taken care all the where the if the car crashes, where the actually stress are going to happen. They have just not calculated. They have just randomly eliminate all the materials. So generative design basically targeted about, we can remove the material, but we need to take care of the stresses where the actual stresses are acting on the model. So it will eliminate the material unwantedly where there is a no role of that material. So it is with the integration of that AI driven generative design of tools. Machine learning for quality assurance, I know, I think you well know, because all the programming. So nowadays you can control the machine through ML. This is a robotic system for post processing. So we have in the industry, we have robots, we have the design of robots, and it is well integrated with the robots for the AI and ML in collaboration with the AI and ML. And the advanced design capability is so complex and lightweight of the structure. As I told you in the generative design, so model will remain complex, but it will lightweight that model structure. And I think you all know better than me, I think. So to manufacture a complex model, it is very difficult for the machining. It is very tough for making a mold. It is very tough for making CNC programs. So what they have done, engineers, they have rapidly take that model, complex design. They will install the same model in the CNC, sorry, 3D printing machine. So by the customized material, so that 3D printing machine will build a model. So for them, so once they will build a model, so they can take the model to the casting for pattern making. So they will take the same model for the casting, and by having a casting, they can start making more models, because they have easily approached the pattern, because without machining we can achieve the sample. So it is complex in the generative design, so we can be able to manufacture the complex models. So topology optimization, efficient material distribution. So I think I already discussed about this efficient material management in the industries. So inventories, related to the inventories, related to the smart manufacturing. So related to the FMS, is a flexible manufacturing system. It plays a very good role there. So next point come with the metal additive manufacturing expansion, increased adoption for high performance application. As I told you about that aircraft, so we can be able to manufacture that wings of the aircraft in the 3D printing. That turbine blades of that aircraft with the you can say that the increased adoption for high performance application. So with the metal or with the composite material, we can directly design the wing of that turbine, and we can able to print that one. So development of high speed cost efficient metal printer. So development of high speed nowadays, earlier it was a big challenge for the 3D printing, because it is a time taking process. But nowadays the engineers, they have, with the help of ultraviolet, UV lights, with the help of that laser beam, they have just performed, they have just increased the speed of that printer. It's a cost efficient metal printers are going to launch in the market. So right now, earlier it was cost near about 4 to 5 crores printer cost for metal printer. But nowadays under 80 lakh, 90 lakh, we can be able to purchase a printer with the high speed, with the low cost printers. So customization and on demand production. So personalized product in fashion, in dental, and in medical sector. I think, because I would like to share my experience. So it is well known for the customization and ready to fit application. Like if some component is failure, and the company just, they have just stopped the production of those component. So in term of phone, you can say, in term of old fans, in term of any antique items, if some component fails from that component, so we can be easily go to the market, and if we try to find out, we can unable to find out that component from the market, and because it is out of order. So in that case, it is well known for the customization again. So we can be create that design, and we can take the printout, and we can directly fit onto the cracking area where there is a failure of the entire component due to this, some sub component. So we can just install the sub component in that, and it is in the field of fashion, and fashion in term of jewelry design. So we can design the jewelry. We can, once we design the jewelry, so we can take the printout by the FDM, and by having a printout, we can be having investment casting. So precise casting. So by taking that 3D printed model of the jewelry, we can be able to make mold for that. And once we are having mold, so we can be easily attain that particular shape of that jewelry. Dental, in the field of dental segment, so very good role is there, because we need to if we see videos from the YouTube, so doctors are rapidly depending upon this design. They have just scanned your cavities, and by scanning the cavities, they will just take a 3D printed model, so in the system. So once they will be having 3D printed model in the system, and by taking that cavities area, they have just filled with the help of 3D modeling. Once they have filled out that 3D model, and your teeth design is ready, and we will take that teeth design, and again that smart materials are there in the 3D printer, so we can just put up the smart materials, and by having that smart material, we can be easily manufacture that teeth of the same, and it will print on the 3D printing, and we can just remove from there and just put up the patient, directly put up to the patient, remove by removing his we can say the that old one, and that damaged teeth, we can replace them with the same one. Is a dental. In the medical sector, I've already clear about that organ pending. So another point already discussed, on demanded spare part, that is already absoluted from the market. So we can be easily printed all those component by having this manufacture of spare part, because we are having customization uh, modules are available. So distributed manufacturing, so decentralized production model, so we can be able to manufacture any type of model anywhere, because in let's say in my industry, if there are 10 printers, so we can be able to manufacture thousands of model at a single time. So these kind of capabilities is also available in the 3D printing. So on-site manufacturing for the remote locations, so that is also possible. So flexibility in supply chain management, so it we can be easily uh, manufacture or easily manage the supply chains. Sustainability and circular economy, so reduce material waste comparative to traditional method. So if you have any question in the reduce, how we can be able to reduce the material with the this waste compared to the traditional method, if someone wants to ask any question, then you are open to ask. Please put any question, because it is well popularly famous in the market just because of this material management. The unwanted, we can say that the unwanted wastage of the material, we can be easily uh, demolish, because uh, we need not to spend much on this, because material is stored in the field of filament. So we can be just put a filament in the or the resin. There are lot many modules are available for the same, because so it reduces the material management. Use of biodegradable and recycled material is also possible. It is a big challenge for the Indian market nowadays to have a biodegradable materials. So that is also possible by the use of 3D printer. Support for circular economy models. So that is also possible, because it plays a very good role for the cost efficient model. So we can be easily attain the cost because let's say if there is some auto component and I need to manufacture one gear, and if we go to the traditional manufacturing, we need to forge it first, then we need to pre-forge it first, then we need to post forge it first, then we will having a turning final OD and ID, then we need to take that gear for the chamfering, tooth chamfering process, for the manufacturing, CNC cutting, hobbing process is there, broaching process is there. And to manufacture a single gear, we need to take care of at least 5 workers and 10 machines. I'm not including the cost. It costs near about, if say 1400 rupees. And by 3D printing, by the having that smart material, we can be easily manufactured with the 500 rupees to 600 rupees. And rapidly we can get it. By the morning, you have design, and by the evening, you will get the same model as whatever you have designed. That is why it is the simply you can say that the economy model you can be able to achieved by the help of the 3D printer. So bioprinting, the future trends is entirely we can be say that the bioprinting and healthcare. So it is in the form of tissues and organ printing, medical implants, heart, gallbladder, kidneys. We can be able to drug development and research application. So in this research application, I already explain you because this is a wider area available in the field of research application. So we can choose one material, and there are we can be able to publish more than 10 paper or 10 or 15 paper on a single material, because the research area is open for this bioprinting, because this is newly invented, and it is an invention last 7 to 6 years. It is in the market. So huge development of the material. So in the new industry, so maybe you are all aware about this construction. So in the construction industries, so lot many buildings, so they are easily be we can design the building by using the civil CAD technologies. So by having a civil CAD or architectural design, we can just design those, and we can be just print those by the help of construction 3D printers. They are large scale printers for building. Food printing, customization, and sustainable food production is also possible. So we can be having a raw material, and we can just print out those foods with the help of 3D printing. Fashion 3D printing in the case of fashion. So near future, uh, these three will be in entire demand is a food printing, because we need not to purchase tomato, we will not to purchase any slices of the component anywhere. We just have a material put up in the printer, we can be customize all those in any sizes. That is also be going to possible by the near future. So fashion 3D printing, it is well known and working in the market nowadays. So we can be easily 3D print the fashion accessories by the use of 3D printers. So standardization and development. So robust standard for the processes and material certification challenges in healthcare. Because I just want to clear you all, because in case of defense component or in case of aircraft component, we need to have a certification from the government regulatory bodies. They will authorize you that your industry or your printer is authorized to manufacture that aircraft or that healthcare uh, product. Then only you can be able to develop all these components. Otherwise, they will take a strict action against you. So it is again uh, regulatory bodies are there, and you need to work with some sort of standards for the development. So additive manufacturing in transforming industry. So emerging trend will redefine production and design processes. Continuous innovation is key for unlocking its full potential. So if you have any question, so you are open to discuss. Thank you very much for your time. So if you have any question, then you may ask. Thank you, sir. Yes, sir. Any question, please?
Dear participants, you're welcome for your questions.
Yes, sir. Harmandeep, sir. Harmandeep, sir. So you want to ask something?
Hello, yes, sir. Good afternoon, sir.
Good afternoon. Harmandeep, sir, you want to ask something?
Yes, sir. Sir, how will biodegradable material impact the industry?
Biodegradable material.
Impact the industry.
Okay. So impact in term of that positive sense or in term of that negative?
Positive, sir. Positive.
Yes, yes. I said, as I told you, it is a huge research area in this biodegradable material. So we can just, let's say, if some patient got injury in his hand or in her hand, so the doctor clearly said that we need to cut it and there is a no replacement. Okay. So
Okay,
in
sir.
that case, so it is nowadays, it is possible, so they can be artificially print all, they can be take the tissues, they can develop a tissues and they will develop a material. So by having 30 days later, they can be able to print that and they will just fit with the customer. So it works. So you check it in the USA, so they have successfully installed 10 to 15 operations. So they are very good and they are working well. Even the transplantation of the heart is also be done in the USA by the help of this 3D printing technology. So you can just check it.
Okay, thank you, sir.
Yes, thank you. Thank you. Yes, any questions, please?
Dear participants, have you any question from your side?
Thank you, Jaskaran ji, for this
Thank you,
good
sir.
presentation.
Thank you very much, sir. Thank you.
We
Thank
feel
you, sir.
obliged you had delivered in such a wonderful talk to our participants and feel that they might be entitled with the knowledge what you have delivered to them. Thank you, sir. Thank you.